Greetings folks, it's Professor Fiore, and in this video we are going to investigate how you can measure the parameters for a JFET. And when I say measure, I mean either in the lab with a real live device, how do you get accurate values, or using a simulator like Tina, which is what I have up right now. So the first thing we're going to look at is JFET characteristic curve, also known as transconductance curve. So there's three parameters we really care about when it comes to biasing and then doing the AC analysis so we can find things like voltage gain. Right? The first one would be the off voltage, VGS off. So what I have plotted here is a normalized gate source voltage. In other words, -1 over here means 100% of VGS off, right? So this is VGS off back to 0 volts. And then on the vertical, we have the normalized drain current. This is normalized to IDSS. Remember, IDSS is your maximum current that occurs at 0 volts for VGS. In other words, literally IDSS means ID, the drain current, with a shorted gate source. That's what the DSS means, right? So this would be 100%, 0%. So here's our curve, all right? So we need those parameters for things like, DC bias. Like, for example, if I had like a self-bias, I need other parameter. The third parameter, the biggie, is GM0, which is the transconductance at VGS equals 0. In other words, that's the slope right at this point up here. What's the slope of this curve, right? So this is a current voltage characteristic. So the question is, what is the change in ID versus the change in VGS off, right? That's the derivative or the slope of this line, and that's what the transconductance is. So GM0 is the slope at this point up here, which is basically IDSS, and at the opposite extreme we have VGS off, right? So if I need that for all my analyses, how do I go about getting those values? Well, you can look them up on a data sheet, but when you do, you immediately see a problem, and that is you'll typically be given a range of values. So they might say, oh, IDSS varies from 4 milliamps to 20 milliamps. Well, that's a pretty big spread. And they might say VGS varies from -2 volts to -8 volts. Same deal, big spread. What do I do? Now you can do extreme examples. In other words, you can do analyses for a very high IDSS and a very low IDSS, things like that. You can also sort of shoot the middle. In other words, they'll also give you a typical value for IDSS, and you could just use that, right? Sort of cross your fingers. But, if you were in lab and you actually wanted to get an accurate value, you're trying to check something out, in terms of the equations, your knowledge of it, how do you really narrow that down so that the ambiguity, the uncertainty is, not a factor of 2 or 3, but it's more like 10%, let's say, something a little bit tighter. Where do we go from there? All right. Well, let's take a close look. All right, so the three things we're looking for here are IDSS, VGS off, and GM0. The first thing I'm going to say is we have this equation that relates GM0, IDSS, and VGS off. So as long as I can get 2 of the 3, I have them all. Right, I can just use this equation. So what I'm going to focus in are the first 2, IDSS and VGS off. If we can get values for these, then I can always compute a value for GM0. Then once I have that, off we go. So we have sort of 2 situations. The first is, how do I get an accurate value out of my simulator? And secondly, how do I do it in the lab? So in the simulator, this turns out to be relatively straightforward. Now, when you grab a device, right, so I've got a couple of JFETs over here, it's not going to come right out and tell you when you dive into the model these parameters. You're going to get some other things which will allow you to calculate those parameters. So, for example, in Tina, VGS off is called the threshold voltage. That's sort of an obvious name. But if you look through the list, you will not find something called IDSS. You will, however, find something called beta, which is not to be confused with the beta of a bipolar transistor. Same name, entirely different thing. This is basically a parameter that describes how steep the transconductance curve is. In other words, I have this normalized curve, but if this was a specific current over here, like a couple of milliamps, let's say, and I have a certain voltage for VGS off, I have another transistor, maybe it has the same VGS off, but its current is, a half or a quarter. It's down here somewhere, okay? So it's a much shallower, slower responding curve. Or I could have the opposite. I could have something that's coming up very, very quickly. All right, so that's what the beta parameter basically tells you. It has units of amps per volt squared. So the bigger this number is, the faster the change. So what you do to find your IDSS is you simply square the total voltage change, which is VGS off, right? It's from 0 down to VGS off. So you square that voltage, you multiply it by the beta parameter, and what you'll get is the IDSS at pinch off. A couple of examples. So I've got a 5458 over here. So I'm going to click on this, and what you want to do is hit the ellipsis right next to it. And I'm going to move this over just a little bit so you can still see that. And here's your list of parameters for this particular model. So you'll see at the very top, the first one here is the threshold voltage, and that's listing at minus 2.88 approximately volts. All right, so I wrote that down. And right next to it is the beta parameter, roughly 488.63 micro, and again, that's in amps per volt squared. Then there's a whole bunch of other parameters. For example, capacitance values between the various pins that we'll use for lag network analysis, things like that. But that's really all we need right now, just that set right there, those two things, okay? Great. Now, what you do is you take those values, right? So you would take that 2.88 volts, square it, multiply it by the beta, at the 488.6 micro, and you'll come up with a value of 4.05 milliamps. Now on the J112, right, different device, so the model's going to have different values in there. The threshold voltage is a negative 2.0556, which I just rounded off to a negative 2.06. And then the beta parameter is 5.696 milliamps per volt squared. So I put that down there. And again, you grind it through, right? Square the voltage, multiply by the beta parameter, and you come up with 24.2 milliamps. Now you could take those two values and you can plug them into this formula and get a GM0 value. Now that you have GM0, you could go and let's say do a self-bias because you need a parameter GM0 times RS, right? The DC source biasing resistor. So you could use a self-bias graph. And obviously, you could use the GM0 to find the GM of the transistor, which we're going to need to find things like voltage gain. All right. So are we done with the simulator? No, we're not done. I'm going to show you a little twist here that you got to deal with. Now, the exact process of doing this in a different simulator, right? I'm not going to come out here and try and get every single simulator. Yours is going to be similar. Usually when you click on a device, there's somewhere in there, there's going to be a button or a slider or something so that you can look at the model. And you go into the model and you find those things. You find the beta parameter and you find the threshold voltage. They might use slightly different names. But, as far as the beta is concerned, I mean, these are the standard, more or less, quote unquote, names, threshold voltage and beta. But if they do use a different symbol, sort of the units are kind of a giveaway. Amps per volt squared is not a common unit. All right, so you could just kind of look for that. But anyway, however you do it, however your particular simulator is set up, you can grab those and get these values. Right? So far, so good. But what's the twist? So the twist is right here. You get the IDSS at pinch off. The question is your circuit actually operating at pinch off? Is that the VDS? Probably not. So we have to remember these, right? These are the drain curves for the JFET. We have VDS across the bottom and ID going up. So the very top curve is the one I'm interested in because that's for VGS equals 0. This current right here, right, here's your VP. And remember, your pinch off is approximately equal to the absolute value of VGS off. So you follow this up, this point right here, that's the IDSS, right? That's what you're calculating in that little formula, right? When you square the voltage and then multiply by beta, this is the number that you're getting. Is that the actual value in the circuit though? Well, if you look at these curves, you realize that they have a slight positive slope. In other words, if we go to a larger and larger VDS, this curve is going up, and therefore the corresponding value of IDSS is increasing. So it can be slightly higher. So what you really want to do is check this for where your particular circuit's biased. You know, if you have a case, let me just go back here. All right, so if you have a transistor like the 5458, and it says the threshold voltage is sitting at negative 2.88 voltage, 2.88 volts. If your circuit is biased where VDS is around 3 volts, well, that's great. You know, things are going to work out fine. But what if the VDS in your circuit's 10 volts or 15 volts, 20 volts? Are you going to get the same value? No, you're not. As we just saw, you're actually going to get a higher IDSS. And if the higher IDSS is then used in this equation, you get a larger GM0, which would lead to a larger GM. So the accuracy starts to go away once you're looking at a larger and larger and larger value for VDS. Okay, so what do we do about that? Well, we turn to this approach. We just build a test circuit. So I actually have two circuits, but really it's just the one. It's really just this one, but I put the two down together just to kind of show this. So over here, what we're going to do is measure IDSS. So I've shorted the gate source, right? I've grounded the gate terminal and I've grounded the source terminal. So VGS here is definitely 0 volts. Just inserted an ammeter and I stuck a power supply in. So this is actually going to set VDS. You would set this power supply to whatever the VDS in your particular circuit is. Right? So I'm just setting it up for 10 volts. Then on the other half of this, what I've done is I've inserted a power supply on the gate. So this is going to set up my VGS. Notice this is negative. The power supply here is shown as positive, but I've put a negative numeric value in. So this really is a negative. If your simulator doesn't let you do this, just flip this power supply upside down. So the negative lead is up here and the positive lead's down here. Right? Either way. And very often when I do circuits here, I'll do it either way. I'll do it one way or the other, whatever my mood is, whatever's convenient. But in any case, so I've got a pair of 5458s in here, and I'm just going to run a simple DC sim and see what we get. So this is what we had before. Right? I just copied this back down. So I'm expecting for my 5458 at pinch off this 4.05 milliamp calculation that we had. All right, so now we go and we run this thing. Do a DC analysis. See what we get off of the ammeter. So I get 4.17 mils for that. So that's the IDSS at 10 volts, right? Now, the ID over here is coming up at this ridiculously small picoamp, 43 picoamps. I don't really care about that value so much. First thing I want to do is come back over here and change this power supply. I'm going to change this to 15 volts. And I'm going to rerun this just to sort of prove a point here. Notice this has popped up to 4.23 milliamps. So at different drain voltages, in this case the source is at ground, so VD is VDS in this case, but at different voltages we do see different currents. Now they're not huge changes, but they are sufficient to slightly alter that GM value that you're going to use, which, could make the difference between having an amplifier with a gain of 19 and one with a gain of, 17.8 or something like that. All right, so it will have an effect. All right, what is the deal with these, ridiculously little picoamp currents that we have over here? Well, if you can't find what the value of VGS off is, you're going to have to play with this number. And my basic rule on this is, in something like a simulator, you're trying to get a voltage. You're going to wait until you get a value such that the drain current is under a nanoamp. Once you're under a nanoamp, or your typical small signal transistors, you're at VGS off, right? So I'll just show you what I mean by that. I'm going to change this by a mere 80 millivolts. So I'm going to go from 2.88 to just 2.8, right? And you would think, well, how much is that going to change? Now remember, last time we had, 30, 40, 50, whatever it was, picoamps, right? Just double-digit picoamps, basically. So all I've done is change that by 80 millivolts. Hey, we're up to microamps. We went from pico to micro. We skipped right over nano, right? So if you don't have a good value for your VGS off, right, you just sit here and you just tweak this a little bit, right? So I go up and I say 2.85. Right? I mean, it would be handy to have a little physical knob here, but it's a simulator, right? Deal with it. All right, so 466.85 nanoamps. Well, I'm still not under a nanoamp, so I'm just going to try that again. Now, if I went a little bit too high, so I'll just put in 8.9, right? You'll see what happens here. I just get this tiny little current. Back it off. Go back to 8.8. Do it again. Okay, still picoamps. So once you get it below nano, and really you don't have to chase this down to like the nearest millivolt. Double digits down here, getting it down to tens of millivolts is usually good enough. Once you get it below a nanoamp, bingo, as far as any kind of accuracy we're concerned with, that'll be good enough for VGS off. Right? So that's just the way this is going to work out. Let me bring back this original 10, and we can actually verify. If you think I'm lying to you, right? So it's still pico, right? So with different voltages, this is going to shift a little bit, but it's not going to be a wholesale shift. It's not going to change by like a factor of 10 or 50 or something like that. You'll see little shifts, right? But as long as you're below a nanoamp, you're good enough. We'll just call that VGS off. So now I can use those values like I did here, right? So I'm going to use 10 volts. So I'm going to say, okay, it's a 4.17 milliamps. That's what I got from my meter over here. Multiply by 2, divided by the VGS off. I get 2.9 millisiemens for my GM0. Right? If these were the J112s that we used before, it would be the same sort of thing. We saw 24.2 milliamps at V pinch off, which was around 2 volts. But now we run it at 10 volts or 15 volts. Trust me, change these. Run the sim, this is what you're going to get. 26.5 mils, 28 mils. Again, you're going to see this slowly increasing effect, right? So it is, in fact, just echoing this, right? Because you're just going up. The VDS is getting bigger and bigger and bigger. You're sort of climbing this little hill, and that current is increasing, all right? But again, we use this. In this case, we happen to find out that we had indeed negative 2.06 volts. Grind the values in here. I just happen to be using 15 volts for this one, so I used the 28 mils, and I come up with 27.2 millisiemens. Beautiful. Now I can use that in my other computations. All right, so I did mention that there's two things: dealing with it in the sim and then dealing with it in the real world. So what do I do in the real world? Well, you get out your transistor, right? So you got some transistor. Maybe it's a 5458, maybe it's a J112, maybe it's an MPF 102, whatever the heck it is. You just build up this circuit. If you know approximately what your VDS is going to be, I've got a circuit. It's going to be somewhere between 10 and 15 volts. All right. Set the power supply up for, 12 volts, let's say. Hook in an ammeter. Set up your FET like this in a breadboard, right? Short these out. Short it back to the negative power supply. Turn it on. Read your ammeter. Done, right? You just a DC ammeter. You read it, and what you're getting is the IDSS at that particular setup voltage, right? And then you could tweak this, up and down to get a range if you were so inclined. And then if you just want to find the VGS off, you just have to add, you take the original circuit and you just add this negative power supply in here, and you just have to adjust this a little bit until current disappears. Now, the only trick here is that your average run-of-the-mill meter, your average run-of-the-mill DMM, is not going to have resolution down to a nanoamp. So, and you got to move this slowly, because if you do sudden sort of jerky motions of the power supply, you can sort of shoot way past what's going on. And if you go the other way, if you accidentally set this up as a positive voltage, you could blow up the FET, because you're going to just forward bias this thing and there's going to be no real current limiting. But in any case, assuming you don't do that, right? You just slowly turn this down piece by piece by piece until you finally get below whatever the measurement resolution is. So, if your finest scale on your meter, let's say you have a 3.5 digit meter and you can read down to, you got like a 1 milliamp scale, okay, 2 milliamp scale. So your resolution there would be 1 microamp. All right, so bring it down until it goes below a microamp, right? When the thing zeroes out, call that your VGS off. Now you have those two values, right? You've got the shorted case for the ID value and this other case for the zero value. You got your VGS off, you've got your IDSS, you can compute the GM0 with the equation we looked at earlier. You're good to go, right? So you use those values. They're going to be more accurate than just using a typical value off of a data sheet, or, just sort of randomly using one of the max min values, okay? All right. Consider this whenever you have to do a real world circuit, or if you want more accuracy on your simulator, all right, compared to your paper calculations. All right, any questions? Leave them in the comments. We'll see you later. Have a good one.